they give us a really flexible means to make predictions. And especially when we start to get into some of the things we'll talk about later in the day, which are things like random forest and the next week with boosting. Very, very flexible tools. So Carolina's gonna start us off and kind of give a background of decision trees, and then I'll take over from there. So Carolina.
Thank you, Tim. Nice to see everyone here connected. And yeah, well, I think that everyone can see my screen. Is that correct? Okay, perfect. So as Tim mentioned, I will start with decision trees in the first part. So the first part, the first definition that is important to have in mind is actually what is machine learning. So here we are actually taking some words of Tom Mitchell, who is actually professor at the Carnegie Mellon University. And he stated in his book, Machine Learning from 1997.
Sorry, Carolina, are you, I might be sharing to a different screen if you're full screen.
Okay. Here. Okay, I will stop sharing again and I will share it once more. I think, is that the presentation now?
Yeah, there we go.
Oh, perfect. Thank you. Thank you, Tim. Okay. So I was saying that Tom Mitchell defined machine learning in his book from 1997, where he said that a computer program is said to learn from experience with respect to some class of tasks and performance measure P. If its performance at tasks in T, as measured by P, improves with experience E. It sounds like a kind of wordy now, but I think that I put here some examples trying to figure out what is that, what does that mean? So for example, if we are talking in this case about experience, we can think on two cases. For example, one in which have images and the second one in which have actually consumption data. So the experience has to do with the data set that we are going to use for actually develop a specific task. In this case, the task is going to be the learning algorithm, which for the first case, in the case of the images, could be something like a classification of images. And for the consumption data that we have, could be something like a predicting any kind of demand. So the performance in this case could be in the first example for the classification of images. For example, the dogs are correctly identified in case that we have images of dogs, cars, cats, and several different images. So in this case, for example, could be like we have the dogs correctly identified. And for the second example, where we have, for example, the predicting demand task based on the consumption data in the data set, we could have something like what is the difference between the predicted and the real value, and that's how we are going to have the measure of the performance. So from this definition, we are going to jump into what are decision trees. So we are going to start with an example to define what is a decision tree. So here we have an example from the Higher School of Economics from Russia. So this is the goal in this case is to determine the proper media. That means that we want to know what is the format that we are going to choose for the publication that we need. So at the end, the labels are, is that a book? Is that an article? Is that part of a book? It's a preprint? Or we should go for contacting the publication or portal news at the university. So in this case, we can see that decision trees are really intuitive algorithms because we have like the labels are something that we really understand. And we are actually just making kind of really intuitive decisions in terms of which are the questions that we are doing here in this case, for example, at the top, for defining at the end what is the format that we need. So here, for example, we are asking, it's this is kind of, yeah, it's analogous to simple if-else logic in programming. Because, for example, in this case, we are asking if that is a monograph, a brochure, a textbook, etc. If that's the case, then we will go that we have a book. So we need the format of a book. Else, we are going to go for it's an article. If that is an article, we go for 3 options. That's going to be mass media, scientific journal, or is that a part of a collection from symposium? In case of that, if that is a mass media, we go to asking if that is not a scientific publication. That case can be published under the section in H from the higher School of Economics in media. And such a case, we have to contact the university. The second case is if that was not a scientific publication, it means that it's a scientific journal. So we go for an article format. And the third option is that it's a part of a collection from symposium. That's going to be at the end a part of a book. And if we don't have any of the other 2 cases, that's going to be other. It may be a preprint if that has a code, for example, an archive. If that it has it, is it yes? So we go for preprint. Other case is no, and we go for contacting publication, the higher School of Economics. So this is the first example, just for giving an intuition how the decision trees work. And in this case, we have a second example. So in this case, some other features of the decision trees. So in this case, we have that. In this case, we are asking our first question. In this case, oh, sorry. What is the goal here? So we are trying to issue loans based on some socioeconomic indicators. So in this case, it's the decision tree is already there. So it has actually this shape. And we have the same thing, right? We are actually asking questions. In this case, we are asking about the age of the individual. So if age is higher or than 40, then we go for the real estate option. If the individual has real estate, we go for issuing a loan. Otherwise, we go for asking for the income. If the income of the individual is more than 5K, we have 2 options that it's going to, if it has, we go for accept the loan and issue the loan. Otherwise, we have for declining the loan. And but before here, we had another option that has to do with what happens when the individual has or is younger than 40. That means that we have to go for asking more questions to try to figure out at the end if we will issue a loan or no. So as you can see, those are like a really descriptive ways in which decision trees work. So from those examples here, we are going to go for the next slide. This is a more formal definition of decision trees, in terms that we need to understand what to learn and understand some of the wording that is important to have the same communication, everyone working with decision trees. So in this case, we start at the top. So we say that we have nodes, for example, in this case, where we are asking actually if, for example, X1 is less than or equal to T1. This is called node. So we have in this case, for example, 1, 2, 3, 4 nodes in this diagram, decision tree diagram. We have the leaves, which are actually the ending parts, which usually are the labels or the final, the result of the decision tree. So they are called leaves. And we have that what is connecting the node and each one of the leaves, in this case, are branches. And another important concept is the depth. So each one of the levels that the tree is growing, we call it the depth of the decision tree. So in this case, we have actually, it's a depth of the depth of the tree is 2. And it's important to take into account which are those parameters to clearly identify them, because at the end we will have to tune them to prevent overfitting and minimization of bias when we start implementing decision trees. Okay, so what happens with some other important features of decision trees? So we saw in the examples before, in the other slides, that actually decision trees utilize a top-down approach, and which is actually known as recursive binary splitting, and that's important to minimize entropy. We will talk about entropy some slides ahead. So just for giving the characteristic here, and this is important. We say that it's a top-down recursive binary splitting because actually we are going from the top to down. Usually it's a way in which we work with, well, we show decision trees. And then we have in the example before, for example, that we have two options, right? We have a question, and then we had two options to go for. For example, having a yes or having a no in terms of the same logic, if, else. Another important thing with decision trees is that they are considered greedy algorithms. What is the meaning of this? So greedy means that decision trees are making the best decision at every node without considering potential future decisions. That means that when we are actually making a question, the decision tree is trying to make the best decision there. And from there is going to, in this case, binary decision trees, we are going left or we are going right in terms of yes or no or any other question that we are doing. And important as well is that this does not necessarily imply that the optimal decision tree, we will have the optimal decision tree in the long run. So just in the moment, that's why they are considered greedy algorithms. Important as well is that these algorithms are well implemented. Now we have like a lot of experience working with them. And in computer science, they have been implemented through, for example, binary search algorithms. And this is important because we really understand them. We have experience working on them in general terms. So that's important as well for taking into our options working with machine learning algorithms to take decision trees as well. One important thing is that they can be considered black box algorithms, but there are options to try to explain when we have really complex models with decision trees. They are tools that we can use for work on the explainability of them. For example, here is cited the M2C gen or the shapely values. And I think this is out of the scope here, but just for naming the tools here. And as well, it's important to consider that they are really lightweight and they are fast as well when we are working with them for implementation with computers. And here, Tim, would you like to add some ideas here?
Sure, yeah. I touched on the productionalization of these models and why they're so effective before, but again, we use these a lot in industry because they're very, very fast, they're very light. They don't take a lot of memory when we're using them. So they can be quite effective. And with the Shapley values and model to code gen, I'll touch on those briefly at the very, very end today if we get there, just in model explainability and feature selection, or feature importance rather.
Okay, thank you, Jim. Okay, and well, now we have a notion of what the decision trees are. So I think it's important to start with some ideas about how do we construct them. So in this case, when we are talking about construction of the decision trees, we have some background that I think is important to mention here. And that is that we take a few key ideas actually from information theory. So that I would just briefly mention that, because I think it's important to understand a little bit more. So information theory is useful to characterize probability distributions or to quantify a similarity between probability distributions. So what is the basic intuition with information theory? It is stated actually that in the, I think is Goodfellow book, it's stated that actually learning that an unlikely event has occurred is more informative than learning that a likely event has occurred. So this basic intuition is important because that gives us a more formal definition about what is that information theory and why it's important for decision trees. They define, to formalize that, a concept called the self-information, where we have that an event, we can know an event can be just defined like the minus logarithm, natural logarithm of the probability of the event happening. So why is important that? Because here we are actually touching one tool that has to do with certainty and the information that we have about any event. So I will try to explain a little bit more in terms of the examples that we had before. So in the slide number 4, in the second example, we have actually the example where we wanted to decide if we would grant a loan based on some features like age, assets, income, and other variables to an individual. So the question here is what we should look at first to know, or which is to know if we are going to develop the right decision tree. That's an important question because at the end, when we have a lot of all the features in our data set, we usually don't know which one is the right decision to start with, because at the end we have just some questions that we have to go through the decision tree. So the decision of the right question at the beginning is important. So in this case, we are just looking at the example of binary trees. So in this case, we have the definition of the Shannon's entropy, which actually is related to the definition that I mentioned before. That has to do, that comes from the information theory. I said that from there, we are actually working with the natural algorithms. So in this case, the Shannon's entropy measurement is defined as you see here in this formula. So we have that the Shannon's entropy is actually the negative sum of the probability of each one of the features that we have multiplied by the logarithm in base 2 multiplied by the probability. So we have here, considering the example in the slide number 4 and considering this definition, how do we try to click them together? So if we go to the slide number 4, I will just go back briefly. We had that the first question here was age, for example. So what do we have here? We are trying to predict where each observation belongs when we have a new value coming here, new value of age coming here. We are trying to predict if that age is above or over 40. So that is that we are trying to get if that observation, that value belongs to the most commonly occurring class of training observations in the region to which it belongs. That means below or over 40 in this case. So we have a lot of uncertainty about that, right? Because we don't know exactly where does that belong to which side of the boundary defined by 40, which is the age we are asking for. So this Shannon's entropy is actually giving us what is the variability in the probability in that binary problem. So when we have, for example, that we have a 50-50 probability, that means that we have a maximum entropy, which is 1. Or for example, if we have 100 and 0 probability, we have a minimum entropy, that means 0. So for example, if we had that in both sides of, or both regions that are defined by the line of the 40, we know that at the end, if we have 50 and 50, that means that we have, there is no clarity which is the class that we have in each side or each of the regions defined by the 40, by the line of the 40 in the case of the H. So that means that we have maximum entropy, which means that we have actually maximum variability or maximum uncertainty. What happens when we have, for example, 100 and 0? That means that, that our entropy is minimum, which is 0, which means that we have like a certainty, because we know that one of the classes corresponds to above 40 or below 40, but we have more certainty about what is the class in that region. And well, in this case, we are actually related to the units that refer to the logarithm. In this case is bits, but well, this is not the so important here. The most important part here is that when we are constructing decision trees, we are actually working with that variability in the probability of the binary problem, for example. If that's above, for example, in the question of the 40, H larger than 40, we're working with that line in which we have two regions that are defined by that 40, number 40. And then we have to define how is the variability in each one of the regions, and that's measured through this Shannon's entropy. And here is the extreme cases that we can have, right? So here we are going to talk about an example, trying to unveil what is inside of that, what I said before, right? I think that example explains a little bit better. So in this case, we are trying to predict the color of a ball based on its position in this figure here. So we have here 20 balls in total, 9 blue balls and 11 yellow balls. So if we pull out a ball, what is the probability of randomly choosing one of them? If that's going to be a blue ball, the probability is actually 9/20, because actually we have 9 balls over 20. That is the whole universe of, or the whole number, the total number of balls in this line, for example. If we are talking about the yellow ball, what should be the probability or of having a yellow ball? That's going to be 11/20, because we have 11 yellow balls over 20. That is actually the whole amount of balls. If we calculate, in this case, entropy, taking the formula from the last slide, we have that the entropy, in this case, entropy 0, it's going to be actually minus 9/20, logarithm base 2 multiplied by 9/20 minus 11/20 logarithm base 2 of 11/20. And that's actually approximately 1. So in this case, as we discussed before, we don't have too much certainty or about what we have there, right? Because actually we have the maximum entropy. So our uncertainty about what we have here, it's actually really high. So we have the extreme case that we define here in this, but I am actually, I have the pointer here. What actually I'm pointing here. So we have this case. What happens if we decide to go for making a first decision? For example, we can split the balls into 2 groups, and we can say that we are dividing that when x is less than or equal than 12. So we have, for example, we define that is true when we are going to the left-hand side, and that's going to be false on the right-hand side, because yeah, on the left-hand side it's going to be just less than or equal than 12, and on the other case that's going to be false. If we calculate the entropy again in this case, we go for the same formula. So we go that when we calculate the entropy in the side, in the left-hand side, that is actually whole, that's a true side, we go that the entropy is here is 0.96. And if we calculate the entropy on the other side here, it's going to be actually 0.6. So why is this changing? Because we are actually following the same logic in which we have that on the left-hand side, we get only 5 yellow balls, and that is divided by 13 because the total number of balls on the left-hand side is 13. And we have 5 yellow. And if we go for the second subtraction here, the second subtraction, that's going to be 8 over 13, because we have just 8 blue balls. If we calculate the same way the other side, we go that in total we have in this case 7 balls. That's the total amount. And if we calculate the yellow, the blue happening is once, and the yellow could be 6 times. So the entropy is actually going to 0.6. If we compare both values, 0.96 and 0.6, we see that with the entropy is 0, we can see that actually the entropy is decreasing. And the interesting question, or the interesting observation here, is which one is actually decreasing more. So at looking at the numbers, we see that the right-hand side is actually decreasing even more. So as we can see here, we have actually more variability on the left-hand side. And this is where we make that conclusion. Entropy is the degree of chaos. I define it like, or I mentioned that uncertainty in the system. So the reduction in that value of entropy is actually called information gain. So that's clear because at the end, on the right-hand side, we have more yellows, so that we have more certain that we can have a yellow ball than on the left-hand side, where we have like a similar number of blue balls and yellow balls. And okay, and from here, we can go for another definition, which is actually the information. How do we define the information gain? So we have here the formula in which we have the formula. We have the entropy 0 minus the sum of n over n multiplied by the entropy in each one of the splitted in the splitting that we go for. So what is Q? Q in this case, lower Q is the number of groups after the split. And here, it's going to be the number of objects from the sample. And we will have actually that the variable Q, higher Q, it's going to be what is the ith value that we are getting. So if we go, for example, that we had before, we have here, what is the meaning of that? So we did the split in the number in X minus less than or equal to 12. So actually Q, higher Q is actually 12, the X being less than or equal to 12. And we have here that we have 13, that was the actual, the number of balls that we have on one side. And we have here 7, that is the number of balls that we had on the right-hand side. And 20 is again just the whole number of balls in the whole data set. So when we go for this formula, we get actually that is 0.16. So the important part here is that our decision tree is going to make decisions in terms of how we maximize the information gain, how we maximize its value. That's actually how the decision tree is trying to find out which is the best question that we should start with, and from there building or constructing the decision tree top to down. That means that actually we are trying to get like the higher or the more certainty through that process. And finally, we have here that what should be the whole process. So before we had just the first split, the first question, but going through the criteria of the information gain, we can see, for example, that the first split was done in 12. And then if we go and continue dividing and that means making some more questions for the following splittings, we try to get at some point then just the same color of the balls in one side and the other color, the other pure color on the other side of the at the end of the tree. So in this case, going in that way, trying to find out which one is the best question that we can do at each time, we go that in this case, it took only 5 questions. We started with this question, x less than or equal to 12. And then we went on the left-hand side for doing that question for 8, on the right-hand side for 18, minus than, less than or equal than 18, and so forth and so on. So here on the bottom part, on the right-hand side, we have that at the end, making such questions, we got at the end, pure yellow on one side and pure blue on the other side. As well here in the main, in the left-hand side, we got at the end that we could label yellow balls on one side and blue balls on the other side. So in this case, the decision tree could go for that in just 5 questions. For at the end, classifying the balls properly and trying to make the best questions in terms of the information gain that we defined before. So that's for the decision trees part. And Tim, I think that for the Gini uncertainty.
Sure. I think I'll just talk to this slide and then we might take a 5-minute break and see if anybody has any questions, and then we can hop into looking some code after that. But
Okay.
Actually, if you want to just keep sharing your screen right now, I'll just talk to this one slide.
Perfect.
So thanks so much, Carolina. That was fantastic. But she touched on Shannon's entropy, which is one way that you'll commonly split classification trees. But another common way is this Gini uncertainty, or Gini impurity, as it's sometimes called. So this is a very similar algorithm, and it can be computed by summing the probability of an item with a label being chosen times the probability of a mistake in categorizing that item. So that means if you took a value from the distribution randomly, but scale to that distribution, and then versus the actual split, that difference would be the Gini uncertainty. It reaches a minimum or 0 when all cases in the node fall into a single target category. So maximizing this criterion is interpreted as maximization of the number of pairs of objects in the same class that are using the same subtree. So we can look at the equation on the top here. S is Shannon's entropy that we just looked at, and then G is the Gini impurity. And so you can see in the end, 2p 1 minus 2p is quite similar to that 1 minus p log 2 1 minus p. So, and I'll show in the code, we can actually look at an example of this where we can see that it just ends up being roughly twice Shannon's entropy. So with that, we're going to take, I think, a 5-minute break, and I'll see you back at 1:42, let's say, 1:43.
I will stop sharing. Is that okay, Jim?
Yep, that's perfect.
Thank you.
I just see a question here just about if in, let's see, where's that example here? If we split, sorry, can everyone see my screen properly here? I also can't see any. Yeah, okay. I'll have to apologize because my dog wants to be a part of this. If it would be technically the same if you split this into 20 separate leaves, theoretically, but you wouldn't construct a decision tree that way. It would be too hard to manage 20 splits at the same time. Generally, what we're going to do is the way it works is you're going to look at the entropy based on a split and what gives you the best information gain at every single split. But we'll get a little further into actual tree construction a little later on. So let's look at the actual code. So like the other times, I'm just going to kick this up in, let's see if I can minimize this. Kick this up in Google Colab. If anybody's not familiar, there's a great Google Chrome plugin where you can just open any GitLab or GitHub notebook in Colab. It's fantastic. You just click on it and it opens up. Okay. Yes, we're going to run it. So let's just do our imports. There we go. So what we're going to do here, we're going to look at Gini. We're going to look at 2 times Gini. I always pronounce it Gini. I don't know if that's properly, but we're going to look at Shannon's entropy and some other things here. And we're going to just see how the two, basically how entropy and Gini relate in a plot. So if we just run this, so what we're looking at here is, so in blue, we have Gini. In orange here, this is 2 times Gini. And in green, that's entropy. So you can see that entropy is basically just 2 times Gini, which we discussed in the previous slide. I think I might have said the opposite, but that's how it works. So for all intents and purposes, they're basically interchangeable. You might get minor differences as a parameter that you could tune when you're building your decision trees. But for all intents and purposes, it's going to be the same uncertainty equation. It might just fit your particular data better in that case. So let's look at an actual example here. So what we're going to do is create a decision tree with some synthetic data, and then see what it does. So this is just, we're going to create some 1s and 0s. So we can actually plot the data here that we have. So this is just going to be a scatter plot of some data. And some of them are going to be 1s and some of them are going to be 0s. And the idea is we're going to try to fit a decision tree to classify this decision space. So the line here is just the line along that general decision space. But so let's try and fit a decision tree here. So we're going to spin up a sklearn tree instance, and this is just the grid data here. So here, this is that we'll instantiate the instance. We're going to use entropy. This is a max tree depth of 3, so we're going to leave this relatively small. And the random state is just a random state. This could be anything. So then we'll fit the data to our instance, and then we'll just make a plot. So we're going to try to plot this so you can actually see the surface of where it's making that decision in the decision tree. There we go. Hopefully this is showing up quite a bit smaller on this computer. Is that, can we even, maybe not. So here we have these the yellow dots and the red dots, and then you can see where it's trying to classify. And it's doing actually a pretty good job of not overfitting. Could have sworn usually That looks pretty good. So we can see the decision and the the misclassified values, but it's doing not a bad job. So we can see this tree cuts the space into 8 rectangles, and it has 8 leaves, each with a rectangle. The tree will make a prediction according to the majority label inside the object. So this is just a way you can visualize your trees. So given that data, it will actually plot out a decision tree plot that you can use to look at. And this can be helpful in some cases. In a lot of cases, like a realistic, if you're trying to make a decision on lots of data and multiple features, it's going to be so big that it's kind of hard to look at. But in some cases, that's quite effective. So with that, I'm going to hop back to our slides. Now let's see, are we having, is this good? Can we see the slides again? Okay, perfect, thank you. Okay, so let's talk about decision tree regressors. So up to this point, we've kind of been talking mostly about classifiers, but a lot of the things that we want to do with decision trees is actually make regression predictions on our data. So rather than applying entropy or uncertainty, we're going to be using either the residual sum of squares or the mean squared error, mean absolute error, something like this, where it's going to actually just look at the residuals of our prediction versus our actuals. Now, finding the best binary partition in terms of this minimum sum of squares is generally computationally infeasible. So if we looked at every single split beforehand, it's going to be so difficult computationally that we can't really do it. So this is where the greedy algorithm comes in. So we're going to look at just the split at every node and try to maximize that based on the features and the data that we have. So if we're just minimizing at that location, it becomes tractable. So what we're doing here, I'm not going to spend too much time going into the actual, in-depth of these algorithms, because for the most part, they're actually so simplified that it doesn't matter all that much. But what we're looking here for is the splitting variable j, so that's our feature, and the split point s, which is the node, and then define the half planes. So then we will solve, or you fit it into this. Where's let's get the pointer here. If we plug that in here, so we're going to try to find the best fit for j and s that solve this equation. So for any choice of j and s, that minimization is solved by the average of y and x that fit into that split. And then for each splitting variable, the determination of the split point can be done very quickly, hence scanning through all the inputs, and finding that best split pair is feasible. So it allows you to utilize a large amount of data and a large amount of features quite well. So when we find the best split, we can then partition that data into 2 regions, just like in the classifications, and then repeat that splitting process on those 2 regions. So again, we find the split for every node and then build a subtree below it, and then continue that through every split until we've minimized the residuals to the point that we find acceptable, essentially. Whoops. Okay, so we're going to look at another example here. Where is that example? There it is. Again, dog is growling. Okay, so in this example, we're going to just define an equation here. It's e to the minus x plus 1.5 times e to the minus x minus 2 squared. And so we're going to we'll add in some noise just to make it a little more realistic. Then we're going to fit a decision tree and see what it looks like. And this will be important later on because we can see the overfitting and then see how bagged trees and random forest behave on similar scenarios. So let's just say we've got 150 training points and we've got 1,000 testing points, and the noise is just going to be 0.1. So we're just defining that. So let's then define our function, which we just talked about. This is just written out using NumPy. And then we're going to generate these samples and noise. So just using that function to create some X and Y test data, test and train data. So here, X train, Y train, X test, Y test, run it through our generator that we just created. Then, like before, let's instantiate a decision tree regressor. We're going to set this time with a max depth of 5 and a random state. And we'll talk about some of these parameters a little later on and how we can tune these, but for now, we'll just say max depth of 5. And then let's fit the training data and make a prediction on our testing data. And then just use matplotlib to make a little plot here. So let's see what this looks like. Great. So in blue, this is our the function. The dots are the data points. So you can see it's the function plus that 10% noise randomly thrown in there. And then the green line is going to be our decision tree regression equation. And so you can see with a lot of decision trees, they're going to be quite jagged, hence all the tree, because it's making a split at every one of these locations. But you can also see this is tending to overfit quite a bit, right? Like it's picking up a lot of the noise. It's not too bad. It's smoothing in some places, but some, aren't quite realistic, especially in sparser areas. But overall, it's not a bad fit. So it's got a mean squared error of 0.02, which is, in this case, not too bad. But if you think about this for a usability perspective, the overfitting can be problematic. And so a lot of what we'll talk about today is going to involve how we reduce overfitting and how we improve just the accuracy of our models by reducing variance. So we're not going to talk about KNN. Just a heads up, that's going to be coming up in a couple of weeks, I think. So yes, even this example, tends to overfit. And so moving forward, we're going to talk about how we can do that, or sorry, get away from that. But let's talk about some crucial tree parameters. So I kind of talked about we talked about the depth and how many leaves. So technically you could build a decision tree until each leaf has only one instance. So this would be a hugely overfit tree. It means you've basically fit the tree to the noise in the data. So you'll end up resulting in partitions on quite meaningless data. It's just splitting on noise just to maximize that information gain and get that very last split that it needs. Examples sort of in line with that first example that Carolina gave the loan application. If it started saying, what were the color of the loan applicant's pants? Well, that's not really applicable. Or the first letter of a baseball pitcher's name. I've seen things like this where it says, pitchers with the first name that starts with P, they pitch better on Wednesdays. And, these are things that intuitively know aren't true, but the decision tree will start to pick out these correlations. Or in oil and gas, I've seen models come back where they say, yeah, the location, the DLS number in the grid makes the biggest contribution to the model, but we know that's not true. That's just that's just a coincidence. So the big exception here when you're building these really deep trees is for things like random forests. So we'll talk about this a little later, but the entire purpose, or what you'll often do with random forests, is to build these super overfitted trees so that they have high variance between multiple trees. Like every decision tree will have quite a fair amount of difference because it's fitting to that noise, but very low bias. So they'll come up with very tightly fit answers. And we'll talk about why that's such an effective strategy when we get to random forests later on. And pruning. So we'll talk about this coming up, but it's often effective to actually build your trees all the way to the bottom and then start removing nodes that have no improvement on the model performance, because the problem with limiting your tree growth is you might be losing potentially good splits later on just because you said, well, this split isn't good enough on this particular node. Okay, so continuing on with overfitting. So here's that example again, and you can start to see where it's starting to overfit this decision space. You know, it's changing the, whoops, pardon me. That pointer, there we go. So it's fitting, no, you can't see it because of the red. Because there are these two data points here, it's saying, well, we've got to make our decision space go along there, and because it can fit one over here, you know, these are not reasonable real world applications, or this is not the way you'd expect. You'd want this to be nice and smooth if you know, to fit a real world problem, and that's just not happening. So, like I mentioned in the last slide, we can artificially limit the depth of the tree, or limit the number of samples in each leaf, or we can limit the number of leaves in general. You could say, you know, we only want 50 leaves, or we only want a depth of 5, like we have been already, or we can just prune the tree, and we'll get into that. So let's talk about limiting the tree depth. So it's tree size as a tuning parameter, and you'll see that in the sklearn API, that as max depth, where you just say don't build it past a certain point, and this should be adaptively chosen from the data. So that means that there's no hard number. Like it's really dependent on the complexity of the data that you're trying to build the tree on. This is, you can tune this based on hyperparameter tuning like a grid search, or just intuitively changing this value until you get something that fits. Or you can split it based on only if you get a decrease in your residuals or decrease in impurity with that split. So in sklearn, there's some parameters like min impurity decrease or min impurity split. So these will take those, it's saying if it's not increasing your, or not decreasing your impurity by say 0.1 at every split, then stop. And then, like I said, you can also limit the tree growth by maximum depth or maximum number of nodes. So let's talk about tree pruning. This is probably the most effective way to limit overfitting in straight decision trees. So rather than limiting the growth of the tree, like we said, it's probably more advisable to just grow it to a very large depth and then prune the nodes and subsequent subtrees that don't add significant reduction of residuals. So the reason this is so effective is because when you prune a node, you're pruning all of the nodes below it. So if you artificially grew it to say level 4, or say this, a better example would see T2 here at level 1. if you said, we only want to grow it to this level, or this split didn't result in that much increase in your predictive power of your model, but this split actually really did. So you can come back afterwards and see which splits are being most effective. But there is a parameter in the sklearn API called cost complexity pruning. And this is a fairly intuitive idea. What you're going to do is you're going to look at your tree, and every tree is made of subtrees. So this is subtree T2. So that means it's being split off of this node T2. And then you've got the remaining tree with that removed. What you'll do is, or what the algorithm does, is looks at your tree, and then, or rather, it looks at the tree, looks at the tree, and it's going to look at the tree minus that subtree. And if there's a decrease in residual, then that subtree is going to be removed. So basically, if your model performs better with that subtree removed, then you've improved that model, and that model, or that tree should be, that subtree should be pruned. There's a lot of good tree puns in decision learning, or decision tree learning. So we can actually define this cost complexity criterion. And what the parameter that you're going to be tuning here is this alpha. So it's a positive float, and what it's going to do is, as long as it as you give a unique value of alpha, you're going to be given a different tree as a result. So it's going to prune in some way your tree. Large values of alpha create smaller trees. So as alpha gets larger and larger, you'll decrease the size of your tree and subsequently reduce your overfitting. But to some point, you're going to reduce your tree accuracy. Your bias is going to increase. And as the notation suggests, so if you have a alpha of 0, then you're just going to end up with the original tree that you grew. So if you're building this, you can do it at 0, and that's just your regular decision tree, or any number above that is going to be some subset of your full tree. And again, just like the other parameters, this is something that you're going to want to tune with your data. There's not going to be a hard number like you shouldn't go higher than X, or you have to be below Y. It's just something that you have to intuitively figure out. So just a few notes on the sklearn API again, because again, this is where most of us use decision trees in Python. So max depth is, like we talked about, the maximum depth of the tree. The max features, so this is if you want to take only a subset of the features for each partition or each split. So this it can potentially reduce overfitting, but more than anything, this is just going to split up, or speed up the training of your model. So if you've got a ton of data and a ton of features, this can help. And there's this feature selection for splits is something that comes into random forest. So we'll talk about that a little more depth later on. Min samples per leaf. So this is a tuning parameter. So if you don't want it to grow to just one sample in every terminal node or leaf, you can say, there needs to be 2 or there needs to be 10. And this again can reduce your overfitting. And so, like I said, these parameters can be set based on the input data, and you want to do it with just cross-validation. So just seeing where your model improves, where it gets worse, and try to tune it that way. Geez, we're flying ahead here. I have to take a little more time. So now we get into the meat of what we want to talk about today, which is ensemble methods. Ensembles are really what make decision trees a viable option in machine learning. And these are, if you're going to be using decision tree methods, it's likely going to be in an ensemble because that's when you really get the benefits. So today we'll talk about bagging or bootstrap aggregation and random forests, which are kind of like a subset of bagging. And next week, I believe, is boosting, which is another fantastic method. But I use these ensemble methods all the time. You know, they're really what give us the benefit in decision trees. So let's define what ensembles are. So it's a set of elements that collectively contribute to the whole. And there's a good analogy for this from a long time ago, the Marquis de Condorcet's jury theorem. So the idea is, if you've got a jury in a trial, if each member of that jury makes an independent judgment, and the probability that that judgment is correct is greater than 50%, then the probability of all of the jury, like all of the decisions of every juror, increases with the number of jurors and tends towards 1. So the concept is that the error of every individual classifier or every individual regressor gets averaged out. However, if the probability is less than 50%, then it has the potential to decrease because you're actually making the model worse with every subsequent addition. So like I said, in ML terms, the accuracy of each model of the ensemble is greater than 50% by some metric. Then aggregating several of these models together will increase the accuracy of the total model. And we can actually show the equations that prove this. Likely if the individual model is less than 50%, then it will actually reduce the accuracy. And then a similar theory here is wisdom of the crowd. But the idea is essentially 2 heads are better than 1, as long as both those heads are working properly. So I was going to take a break here, but I don't think I will because we're actually kind of motoring through. You know what, I might, let's see, I thought I saw there might have been some questions here.
Yeah, there are 3 questions right now, and 2 of them is for tree pruning, and the other one is like my question about regress tree, but you don't have to answer it if it takes too much time. I'll just talk about the tree pruning questions first. So
Sure.
the first question is from Lei. He asks, in tree pruning, does it look at the residuals of training data set or the testing data set?
It looks at, now is it? It's no, because it's built into it's looking at your training data set, the residual in the training data set. But this is something, well, it's something that you're going to want to tune yourself, so it'll be in the testing data set. So as you're if you're pruning if you're pruning your tree, you're going to be looking at the uptick in performance of your model based on your alpha, say. So as you change that alpha, you'll be able to see that increase or decrease in your model performance.
Okay, thank you. And the second question is from Khaled Al-Amudi. He asks, is tree pruning computationally expensive? Because you generate a large tree, then test the residuals after removing a part of the tree, right?
It's not bad. I don't know the actual like I don't know the big O notation of tree pruning, but it's not bad. You know, if you were going to do pruning on, say, an ensemble method, which doesn't really make sense, and we'll get into why, but if you had hundreds or thousands of trees that we were trying to prune on, then it could start to get expensive. But no,
Usually,
it's not too bad.
okay. So it usually worth it if you have like one tree, but if you use a lot of trees, you can just use ensemble.
Yeah. So when you're pruning, you're generally going to be doing it on just one tree, and the performance uptick is going to be quite significant for most trees, because if you're going to be pruning trees, you're probably going to be building them to maximum depth and then pruning. So it's going to improve the performance or the generalization of your model quite a bit.
Okay, thank you.
Yeah. So with that, we can, we can talk about bootstrapping. So bootstrapping is probably my favorite part of statistics. The idea is that you have a certain sample of your data, and then you can also take bootstrapped samples of, which are smaller subsets of your input sample set, and then take new statistics from those. The nice thing about bootstrapping is that it allows you to get better statistics on the distribution of your input set from relatively small samples. So you can, there are examples that I've used it where you've got a very small, like you could have, say, 30 samples, but when you look at the distribution, there's just not enough data to get a good confidence in your distribution. So you can bootstrap, which is, now I think we have the actual, I think it's in here somewhere, but it's sampling with replacement. So in this case, we've got a certain number, and you can see in this case, there's 2 purples. It's sampling the purple one twice, but that's okay because it tends to even out. So if we did, in this case, there's 3 samples, but we could do hundreds of bootstrap samples and then combine them together to get, the mean and mode and standard deviations of this bootstrap distribution. The idea lends itself very well to bootstrap aggregation models. So this is where the term bagging comes from. It's just portmanteau of bootstrap and aggregation. So suppose we have a training set X or chi, depends on how you want to look at it. I'll probably just end up saying X, so I'm going to read it. Using bootstrapping, we can generate multiple samples from that original training set, up from X1 up to Xn. So for each bootstrap sample, we can train its own classifier. We'll denote it A1 of X. And the final classifier will average all of the outputs from these individual classifiers. In the case of classification, this corresponds to voting. So in classifiers, you'll call them votes, and then in regression, it'll be averaging the predictors or averaging the residuals. So we can see here's that equation where it's 1 over m, the sum from 1 to m of those individual models. And from sort of the diagram of that, we've got the training examples, and we're going to take one test sample with replacement, train a model, create a classifier. We're going to do that several times, combine them, and then use that to make a prediction on some new data. Now, let's get into the actual math behind why this works. So let's consider a regression problem with a bunch of different base algorithms. And we're going to assume that there is a true function for this, y of x, sort of like in our previous examples with the regression problem, where we had a true function that we were trying to solve. And that's defined for all the inputs, and the distribution p of x is defined. We can express the error for the regression as just that difference between the regression or the prediction versus the actual target function. So the expected value from that mean squared error is the mean squared error. Simple enough. Then we can plug that into all the regression functions and sum that over all regression functions, and then create a new regression function that averages the values from all the individual functions. So this 1 over n now is quite important, and that'll come up in a bit. So the mean squared error for all of these, we can work our way through, but the real important thing is when we get down to the very end that everything cancels out as 1 over n of the error. So the big takeaway here is that by averaging every one of those individual errors, we've reduced the mean squared error by a factor of n. So the idea here is the more models that we add, the more that we can reduce our error. And there's some caveats here that we'll get into, but it's a pretty powerful paradigm for these decision trees, where you can say we have a decent amount of variance between our models, but if everything is well distributed, then we can cancel that error out. So bagging reduces the variance of the classifier by reducing the difference or decreasing the difference in error when we train the model on different data sets. And those different data sets are these bootstrapped sample sets that we use to train each individual decision tree. In other words, bagging prevents overfitting. And because each individual overfit tree cancels out the other overfitting. The efficiency of bagging comes from the fact that the individual models are quite different due to their different training data, as we talked about, and their errors cancel each other out. Another big point here is outliers are likely omitted. So if you have a lot of, or even just some outliers in your data set, they only have 1 over m, say if m is the size of your training set, chance of being included in any given bootstrap sample. So in many cases, those outliers just won't be included, so they won't have a chance to skew your model, which is very powerful. So scikit-learn has a bagging regressor and bagging classifier model. And the nice thing about these is you can plug in most other algorithms as a base. It'll just bootstrap any individual model. It doesn't necessarily have to be a tree. But this works quite well with trees because of the way they're designed and that high variance, low bias when they're built right to the maximum depth. So we can compare a couple of examples here. This is straight from actually sklearn's documentation. So on the left, we have an individual decision tree, and you can see where it's overfit to the data, but also where we're mapping out the, sorry, this is the actual equation. When here we're mapping out the error and the bias squared and the variance. So in this case, we have a decent amount of bias, but if we look at the bagged trees, we've reduced the bias slightly, arguably, but the variance quite a bit and the error quite a bit. So this is where you can see the bias to begin with was quite low because we've built these maximum depth decision trees. But we haven't really introduced much additional bias, but we've reduced our error and variance quite a bit. So as we, and I don't know in this particular case how many models are bootstrapped together, but, or sorry, aggregated together, how many bootstrapped models are aggregated together, but you can expect that error reduction to be proportional to the number of models to a point. And like we talked about before, bagging is quite effective on these small data sets because you can create multiple training sets from your small data set to begin with. And the nice thing is that every individual bootstrapped sample is going to have quite a bit of variance, especially on small data sets. So it's going to be able to capture that noise quite well. If you have a very large data set, you can just build this from a much, you can just create smaller sample size, or it's still going to work quite well. But I do use this quite frequently on very small input sets. You know, if there are only a couple hundred inputs, this gives you a nice method to reduce overfitting and still get a good predictor on a small set. So let's talk about how we build bagged trees. So to apply this bagging to regression trees, we simply construct B regression trees using B bootstrap training sets and average the resulting predictions. Simple enough. The point of this is to grow these trees to their maximum depth and not prune them. So we have high variance but low bias. So we are able to capture that noise that we can then cancel out. So averaging the B trees reduces the variance in the entire model. And we've seen that a few times now. Bagging has been demonstrated to give impressive improvements in accuracy. And you can use this on hundreds or thousands of trees in a single procedure. I would caution that you're going to see reduced improvement after a certain number of individual trees. There's going to be a limit to the gains that you can improve, and we'll be able to talk about that with the independent distributions of your input sets in a bit here. Right, so I guess we're talking about right now. That previous example is good, but it's not necessarily applicable to what we're going to do in real life, because it makes the assumption that our individual errors are independent and identically distributed. That's kind of a fundamental part of bootstrapping, that your errors are independent and the distributions are identical. The reality is these errors are likely correlated, and your the error reduction is not going to be as significant. You'll probably and almost certainly have some reduction of error. It's just not going to completely capture all of your noise and solve all your problems. It's just not the way it works. But later on, we'll in some of the subsequent lectures and subsequent weeks, we'll talk about some other methods that are a little more sophisticated, which give more accurate predictions in real world problems. And we'll touch on one coming up here in random forests. Now this does reference random forests, but this works with ensemble methods. So I'm just going to touch on out of bag error. And so what this is with ensemble methods, with bagged methods rather, you don't explicitly need to use cross-validation, which can be very powerful. It means you don't have to reduce your actual sample size in order to make a training and testing data set, which is why it can be so powerful on really small samples. The reason for this is because these bootstrapped samples kind of take this into account internally by only using part of the sample set in building every bootstrapped subset. So in the case of random trees, which we'll talk about coming up, these are constructed with different bootstrap samples of the original data set. And for every individual bootstrap sample, approximately 37%, it's like 36.67, I can't remember, of the inputs are left out. So you're left with only about 63%. And we can show that, which is, if say you have L number of samples in a data set, at each step, each data point has an equal probability of ending up in that bootstrap sample with replacement, which is important. So the probability becomes 1 over L for every individual sample point. The probability that no bootstrap sample contains a particular data set element or a constituent, say a particular sample. So the odds that it's been omitted L times equals to 1 minus 1 over L to the power L. So as L approaches infinity, it becomes equal to the second remarkable limit, which, if you're familiar with from physics, is 1 over E. So then the probability of selecting a specific sample for every bootstrap sample is 1 minus 1 over E, which is 63%. Not super important to know, but it's nice to know that you're building in that train test split automatically. It kind of ends up working like a k-folds cross-validation. Now, whether or not it's still prudent to do a train test split, I would argue that it is. It gives you that extra validation check when you're building your models, and allows you to just tune your model a little better. So I would always suggest that you still use cross-validation of some kind, but it's not explicitly necessary because it's built into these equations. And like I said, if you've got a really small sample set and it's going to really affect your training, if you reduce it by 30%, say, this can be quite powerful. So we talked about this, in the last slide. So just a visualization of this is how you can see where this can be effective in splitting up your data into different bootstrap samples. We went into this quite a bit last slide, so I won't dwell too much on this, but each base algorithm then is trained on 60% of the original examples and can be validated on the remaining 30%, 37% rather. So the out of the bag estimate becomes nothing more than the mean estimate from these base algorithms on those 37%. So you can output the out of bag estimate from the sklearn bagging models or random forest to get this estimate, and it's just averaging that error over all of your trees. Cool. I'm going to we'll take a quick break and we'll look at some of the questions here. Probably a 10-minute break. And then we'll get back to it. We can talk about random forests and look at some more code. And then we'll briefly touch on feature importance at the end. So I'll see, what's the time? 2:33. So we'll be back at 2:43, say. Where was that? Okay, we go. So we do have a question. Pardon me. Sorry, just 1 second. Okay. I don't think I'm muted. Okay. So one question here is, how do you decide the number of bootstrap iterations and the size of the sample? So the iterations is, oh, here, I'll turn my, I apologize because it's really fighting me when I have my screen sharing on. Can't really control Zoom very well. There we go. There's my screen. Start sharing again. So anyway, the question was about the number of iterations, or the number of models in your bootstrap or your bagging. So that's something that you're just going to want to test. It's like any other hyperparameter. There's no good number, I would say. After a certain amount, you're going to, it's going to level off asymptotically, and you just won't get any more improvement. But you know, that might be 50 trees, it might be 100, it might be 10,000. I'd be surprised if it were 10,000, but it really depends on the data that you're working with. And it is still quite possible to overfit your model. So, and the more trees that you include in your model, the more chance you're going to have of overfitting that. And then in terms of the sample size, that's actually just, that's built in. So when you're, it's that 1 over 1 minus E, which is that 63%, which is, that's just built into your out of bag error. But if you're going to be cross-validating on top of that, I usually do, 20 or 30% holdout for test data. I think that was the only question, right? Cool. Then we can talk about random forests. So random forests are definitely, whoops, pardon me. Random forests are probably the best part of these ensemble methods, or for bagging methods. And these are the ones that, if you're going to be doing this, you're likely going to be using a random forest. I frequently use random forests, and we'll talk about why they're so effective over just straight bagged regressors or bagged classifiers. So the problem with bagged trees themselves is that if you have really dominant features, they're still going to control the first few splits, and your trees are going to end up looking very similar. So if you're going to average similar trees, you're not really getting that benefit for error reduction. So the idea with a random forest is you're going to take your same bagged model, your bootstrap aggregated decision tree in this case, and you're going to also randomly split on individual features for every split. So rather than taking a selection of all of your features, you're going to just say, you know, for instance, the square root of the number of features, and you can only choose from those ones. The idea there is it allows you to decorrelate your individual trees, and it allows you to introduce some potential noise. You're going to be trading off a little bit of bias in your individual trees, but there'll be more, it'll better capture the noise in your data set, and you'll be able to average that out better. So like you said, when building the individual trees, each time you consider a split, only a random sample of predictors is chosen at that split. And that random split selection is reset every time you make a split. So you're not stuck with those random variables or those random features for all the way down the tree. So typically, yeah, like I said, typically we'll choose the square root of the number of features, but you can also use, you know, there's log, you can set and just, you know, I only want to use 5 or I only want to use 10 of my features. And that's something you can tune as a hyperparameter. But the smaller the number, the more noise, or sorry, the more randomness you're going to introduce into your random forest. And that's where the term random forest comes from. So in other words, when you're building this random forest at each split of the tree, the algorithm is not even allowed to consider the majority of the available predictors. So that's where the randomness comes from. Using a small value of m, building a random forest will typically be helpful when we have a large number of correlated predictors. So there's another benefit there, is you can use highly correlated features where, and it won't cause as much of an effect. I won't say it won't cause any effect, because there's an opinion that's, I think, a wrong opinion out there that you can just throw everything you have at a random forest and expect a good result. But there's still going to be some issues with autocorrelated features, but not as much, say, as like a linear regression, where that can easily cause some problems. So let's look at some code. Make sure that we're all good. So let's do all of our, let's load all our models. In this case, we're going to be looking at the random forest regressor and random forest classifier, bagging and classifier and bagging regressor, and then comparing that to the actual decision tree versions. And then our other favorites like train test split. So again, so this is going back to that initial example with the decision tree. We're going to just make that same data set where we're going to try to fit this same equation. But in this time, we're going to instantiate the decision tree to regressor, but we're also going to create a bagged version of that same regressor. So it's just adding on the bagging component to that same model. And then we're also going to fit a random forest. So and then we'll be able to compare how these fit the data. There's also going to be the plot title for every one of these is going to be the mean squared error for each, so we can see how that error improves. So let's run this block of code. There we go. So let's look. So the decision tree, you can see, like we had before, quite a bit of overfitting. It's matching the noise in the data almost perfectly. So not great. And we've got a mean squared error of 22.76. But if we looked at the bag, bagged model, so this is the same decision tree, but just bagged, you can start to see where it's not overfitting as bad. We've reduced our mean squared error quite a bit, and overall it just looks better. Great. So let's look at the random forest version. We've again reduced our mean squared error a little bit, and it's again not overfitting nearly as much. It's still overfitting, and this is something that you'd probably want to tune with your parameters, but when you're taking just the input model that you're given and bagging versus the individual, or the random forest versus the individual, you can see the improvements in that model performance. So we can also look at the advantages of these random forests on classification problems. So we're going to do something quite similar to what we did before. We're going to create those circles, the random circles, and then we're going to fit a bagging classifier and a random forest classifier. So if we run this, now we get our 3 printouts. So with the decision tree, there's again these heavily overfit areas where you can see which data points are pulling over these sections and giving you this very irregular decision space. Not great, but it's still, it's something you could make predictions on. It would be noisy, but it would still work. Now, if we look at the decision tree for the bag decision tree, rather, you can see where it starts to smooth out. We're losing those big spikes where it's overfit to the edges. And there's still a few blobs, and it's still a little irregular, but it's looking quite a bit better. You compare those two. And then looking at the random forest, there's maybe some slight improvement, arguably, but it's it's in line with the bagging. But I think that's showing that we've got a very good improvement when we look at bagged algorithms. So if we jump back, we're going to just look at a few of the parameters that go into building these. Oh no, wait, first let's talk about, sorry, my some of my stuff got turned around here, but we can talk about variance and decorrelation for the time being. So the main problem with decision trees is that high variance. A small change in the data can result in a very different series of splits, which it's something that we take advantage of in the bagging process, but it can be very unstable. The major reason for this instability is the hierarchical, it's a hard word to say, nature of the process. So the effect of an error in the top split, it gets propagated all the way down to all the splits below it. So just like it said, if there's something goes wrong with that very first split, the entire tree is basically struggling to keep up with that for the rest of the model. So one way we can alleviate that is by trying to use a more stable split criterion, but it's kind of inherent to decision trees. It's just basically the way they're set up that as a sort of almost like a directed graph, you can't change what's happened before. So we can look at the actual variance of a random forest, and I won't dive too much into the individual equations or talk them out, but we can see the correlation of these two trees, essentially, where rho of x is the correlation between any two trees using averaging. Theta 1z and theta 2z are randomly selected pair of trees or randomly selected elements of the sample. And this T of X theta Z is the output of the ith tree classifier. So this is basically an individual tree. Sigma squared of X is the sample variance of any randomly selected tree. So this is the variance of that specific, any given tree that you're selecting. Just as a note, it's easy to confuse rho of X with the average correlation between trained trees in a random forest when we consider these trees as n vectors and calculate the pairwise correlation between them, but it's not necessarily the case. The correlation it's related to that averaging process, and there's a dependence of rho of X on X that warns of that difference. So when you think of rho of X, it's actually just the theoretical correlation between a pair of random trees in that input, not necessarily two specific trees. And its value comes from that repeated sampling of the training set of the population Z, and the random sampling of the trees. In stats jargon, this is the correlation caused by the sampling distribution of Z and theta. You don't have to worry too much about that. It's something you might want to keep in mind. So we can look at the conditional covariance here. So the conditional covariance of any pair of trees is equal to 0 if bootstrapping and feature selection are independent and identically distributed. So that was that kind of caveat we talked about earlier about things being IID, as it's commonly described. We know that this isn't necessarily the case. So if we consider the variance of a single tree on the left versus the variance of a random forest, you can see that the variance of the tree on the left is much higher. So we can see just in terms of the scale here, the total variance of the tree gets up to, say, 2.0 versus in this case, it's down, below 0.8. Or sorry, on the right, that's the mean squared error. The variance itself here, it's 0.12. So it's considerably lower in this example in the random forest. Let's talk about bias just a little bit. So in bagging, the bias of the random forest is the same as that of the single tree. In absolute value, the bias is generally higher than that of an unpruned tree. That is, it's not as explicitly accurate as an unpruned individual tree because of the randomization that we introduced into the random forest, and the sample space reduction by bagging. So, but the introduction of bias won't be considerable. So the improvements in the prediction accuracy obtained by bagging in or random forest, it's solely a result of the reduction of variance. So that averaging of models reduces the variance of our final model. So there's another subset of random forests called extremely random trees. So this is taking random forests to the next level, essentially, based on the randomization of those features that you're looking at. So it just employs a greater degree of randomization at each split. So instead of searching for the optimal threshold in between all of those selected features, it just takes it's just selected at random, essentially, for each possible feature, and then the best one among those is used. So it's another degree of randomness that's added on top of the random forest. So this will increase the bias of your model by introducing purposefully inaccuracy, but that randomness then aids in getting canceled out further, and you should reduce the variance of your final model. These are really effective if you have overfit with a random forest. And this week I was trying to prove this point. I was going to try to show something, but I can't. But because of there's a lot of talk, even in these slides and in the information that we're giving you, that makes it seem that random forests are kind of infallible and they don't overfit because we've introduced all of these randomization parameters. But you can absolutely overfit a random forest. So I don't want to impart you with the opinion that that's not going to happen. But extra random trees can help with that. They can, it gives you extra parameters to tune, and you can hopefully reduce some of that overfitting. So this is something, this is in the GitHub notes, and it's something that I never personally used, but I know you can use this random trees embedding as a way to classify some of your data for unsupervised learning. What it's doing is it's transforming the data set into a higher dimensional sparse representation of your input set. So what you do is you build extremely random trees or extra random trees. Then you can use the index of the leaf containing each example as a new feature as a classifier. So for example, if the input appears in leaf 1, or sorry, in the first leaf, we assign it 1, and then if not, it's assigned 0. So you can control the number of features and the sparseness of the data by increasing or decreasing the number of trees and their depth. Basically, tuning how your random forest works will control that. And because nearby data points are likely to fall into the same leaf, that transformation provides implicit non-parametric estimate of the density. So it's just something you can try for non-parametric embedding or classification of your data if it's not trained. So let's talk about some of the pros and cons of random forests. This is kind of a bit of a summary slide for random forests. So a big plus here is the high prediction accuracy. These random forests tend to perform better than linear algorithms in a lot of problems, or this says most problems. We'll touch on a couple of things where they don't, but they're really good. The accuracy is comparable with boosting, just regular boosted trees. It's very robust to outliers. This is one of my favorite aspects of these. They allow you to take bootstrapped subsamples of your input data, and that greatly reduces your the influence of any possible outliers. Insensitive to scaling features, the scaling of features as well as other monotonic transformations due to random subspace selection. Doesn't require fine-grained parameter tuning, works quite well out of the box. This is arguable. You can, I think it's worthwhile to tune any model, but 0.5 to 3% gain, you might be able to get more than that, I would say. But again, you have to be concerned about overfitting your data if you're trying to tune it too much. And obviously this depends on the problem and the data and what you're trying to do. So efficient for data sets with a large number of features and classes. This is very true. Sometimes, or oftentimes, people will use random forest to just throw everything into the model and see what sticks. It can be good, it can be bad, but it can, if you work with feature importance, this can also help you kind of figure out which features are doing most of the heavy lifting. And you don't have to worry as much about having too many features and too many correlated features because of the way random forests work. Handles continuous and discrete variables equally well. Not much to say on that one. Rarely overfits. Again, so these are all coming straight out of the GitHub. I would argue that that's not necessarily the case, because if used improperly, you can overfit absolutely anything. But in practice, the increase in the number of trees almost always improves the composition to a point. And tuning your model will show kind of where that maximum number of trees should be, where you get the most gain for not as much computing power. Because the issue with this is if you start really increasing your trees, if it takes 5 seconds to set to fit a model, and then it takes, I don't know, however many, 10 seconds, you're looking at 500 seconds, or 50 seconds, sorry. Or if it takes 100 seconds, then you're looking at 500 seconds. Or it really magnifies the time it takes to train your model. And in some cases, in cases that I've worked on, it can take a really, really long time and makes it really tough to iterate on your model to get the best outcome. There are developed methods for estimating feature importance. So individual trees, it makes it not too difficult to see which features are most important. But if you've got a random forest of 100 trees, or especially an extra random forest, it can be difficult to see which features are doing most of the work. And we're going to touch on this in a section in a bit. But something to note, it's not a lost cause. You can't just, it's not as easy as, say, a linear model. You can just look at the coefficients, but there are methods. It works well with missing data and maintains good accuracy even when a large part of the data is missing. So if you're potentially missing certain features, it'll just use other features, or it can use other features. You kind of have to work with that, but it's quite possible. Provides means to weight classes on the whole data set as well as each tree sample. Yeah, kind of talked about that a little bit. Under the hood, it calculates the proximities between pairs of examples and can subsequently be used in clustering, outlier detection, and other interesting data representations. So you can kind of tweak this to fit the needs of what you want. There's other ways you can tweak decision trees to get other things out of them other than just predictions or classifications. And the above functionality and properties may be extended to unlabeled data to enable unsupervised clustering, data visualization, and outlier detection. It's kind of a similar thing, but like we touched on briefly with unsupervised classification. Easily parallelized and highly scalable. This is quite true. And this is somewhat true of all ensemble methods, but parallelization is pretty easy, and it's built into a lot of these packages. Specifically, I know we'll talk about XGBoost in subsequent lectures, but this is important. If you've got a really big model with lots of data, say thousands of trees and very deep individual trees, it could take a very long time. Like, I've had models recently, like this week, where I had to just let it run overnight while it was training. So parallelization makes that much more feasible. So some downsides to random forests. So in comparisons with a single tree, its output is more difficult to interpret. And we touched on that, where you know, you got 1,000 trees, it's kind of difficult to say which features are really driving your output, but we'll talk about some of those. There's no formal p-values for feature significance. Again, we can get around that with Shapley and some other things. Performs worse than linear models in the case of sparse data, text inputs, bag of words. So there's a bunch of use cases where you probably wouldn't use this. And particularly like this next one, unlike linear regression, it's unable to extrapolate. So it's really confined to the data that you have to train on. And you have to be cognizant that your input data is representative of what you're going to try to predict. If it's not, you're probably going to have a hard time. If it's a classifier, you know, it might just say greater than this value, you're going to be, you know, it's going to give you this, but it won't have the granularity that you might want. It's prone to overfitting in some problems. I think I've touched on this numerous times, especially when dealing with noisy data. And I mean, that's true of almost any predictor when you're dealing with noisy data. If that noise is too considerable, it's going to just start fitting your model to the noise. In the case of categorical variables with varying level numbers, random forests favor variables with greater number of levels. This is important to note. So I'll give an example where, say you've got a one feature that is binary, so you just have 0 or 1, and then another feature where it's got, say, 10 one-hot encoded feature classes in that feature. When it splits on the feature with 10 classes, it's going to get more information gain per split. So it's going to, the algorithm is going to tend to favor those. So it's something, not necessarily something that you can avoid unless you can feature engineer your features to get around this. It's not always possible, but it's just something to keep in mind that it may be artificially favoring certain features over others because of this. If a data set contains groups of correlated features, preference might be given to groups of smaller size. And the resulting model is large and requires a lot of RAM. Yeah, so if you're building thousands of trees, they all have to be held in RAM. It can get really big and you can run into out of memory errors. This has happened to me, especially if I'm trying to train or do parameter tuning with something like grid search on big random forests. And then you just run out of memory because it's, you know, you're giving it some crazy values and it just can't handle it. So kind of getting near the end of my presentation. I'm probably going to finish a little quickly, but hopefully we'll have time for questions. So let's talk about feature importance, because we discussed how it's not quite as intuitive with ensemble methods like this. So we've showed this picture on the left a few times, this example tree. And if you're looking at this individual tree, it's quite obvious, you know, the closer feature is to the root of the tree on average, like, oops, like age here, the more important that feature generally is. And this is formally explained by the concept of information gain, which we discussed, or Carolina went over. But the problem is when you've got thousands of these, it can be a little tougher. So, but on average, the closer that feature is to the root means the more significant it is for a given classification or regression problem. Now, There are a bunch of different methods to assess feature importances. Leo Breinman, you'll see this name come up quite a bit. This paper is referenced quite a bit. His work suggested that to evaluate the importance of a variable by measuring the decrease of accuracy of the forest when the variable is randomly permutated or decrease of variables. Sorry, I didn't write this, and it's now confusing now that I read it. This is the concept of permutation importance. So you're just looking at the decrease of accuracy of the model when that that feature is removed. Fairly easy to grasp. And then, right, so we can get into this a little bit. So the average reduction in accuracy caused by the variable is determined during the calculation of the out of bag error. So as we discussed before, that the greater that reduction, which is caused by exclusion or permutation of the variable, the higher its importance. So if you have a feature and you remove it from your model and your model's accuracy decreases by 20%, then you know that it's got an importance tied to it of 20%. So if you iterate through this and take every permutation of features, you can work out their relative importance. There's also another method that sklearn uses in their models, which is to look at the information gain of every node, sorry, every split, basically, and see which features give the most information gain. So what it'll do is look at that gain and then sum them all and normalize it throughout the model and use that as a way to get feature importance. Where was I? So the average reduction in the impurity, or MSE for regression, represents the contribution for each feature to the homogeneity of the nodes in the model. That's what I was saying. So each time the selected feature is used for the splitting, the impurity of the child nodes is calculated and compared with that of the original node. So you can see how much it actually improved. So one of the first things we talked about was this Gini impurity or Gini uncertainty. So it's a score of homogeneity. We saw that the plots where we compared Gini to Shannon's entropy. And that varies from 0, which is homogeneous, to 1, heterogeneous. So those changes in the splitting criterion are accumulated, so they're summed and then normalized for the number of splits, and then that gives you your reduction. So I guess that's just reiterating what I said before. So this results in features, the highest features have the nodes with the highest purity on their splits. So I think the last thing I'm going to talk about here is Shapley values. So this is something that's really gaining traction in the data science industry, and we're using this quite a bit in our work, and I've seen quite a few presentations on companies using this as not only a way to interpret their models, but also just simply a product to give to users. So Shapley, or SHAP, refers to Shapley additive explanations. And these utilize concepts from game theory to calculate the contribution of every feature to the model. This is essentially, what it means is it'll look at every individual feature and decide how much it's contributing, positive or negative, to the final output. And this is really effective for random forests and ensemble methods, but also if you're looking at, I've used this for linear models where you're doing a lot of transforms. So say it becomes like a polynomial transform, and it's difficult to say what features are contributing because your coefficients are getting added to every individual polynomial coefficient. It just gets hard to do. So if you do Shapley values, you can just get overall feature importance from the original input features. So there's a package based on this called TreeShap, which it's a variant of SHAP for tree-based machine learning models. The caveat here is you can sometimes produce some weird results if you have correlated features. So they may not be an issue with your model itself, but sometimes what can happen is you've got two features that are correlated. One feature is quite important, but the other isn't. And just because they're correlated together, it assigns feature importance to the unimportant variable as well. It's something to keep in mind. It's not something I would necessarily worry about because correlated features tend to have a similar importance to your model a lot of the time. But it's just something that you should keep in mind when you're using this TreeShap. So in summary, for Shapley, these are they're very useful for communicating the feature importance of a complex model, and they're not limited to just these ensemble methods. You can use them for quite a few things. But like I said, they can be an important product in of themselves, and because oftentimes we'll say, okay, well, here's the prediction that comes out of the model that we've provided, but also a value is to say these are the features that are really controlling this. So if it's, for instance, an oil field company, and they want not only do they want a value for some well, they also want to know what's controlling the performance of this well, because maybe they can use that to extrapolate to other wells or change the way they operate. And I think that's it. So here's a couple of these. So we've shared these two GitHub pages, which have these, which most of the notes are from. Also, this book, Introduction to Statistical Learning, is fantastic. There's a couple of versions of them. They're slightly different. And I've used both when building this, although I only grabbed a reference for the one. Yeah, they're very good at explaining some of these concepts in a very reasonable way. So let's see here if we have any questions. So let's, this first one here, what does logistic regression achieve similar purpose as a decision tree? So the logistic regression would be similar in purpose to a decision tree classifier or a random forest classifier, or et cetera, where you're trying to classify. But the way they go about these is different. So they'll have different use cases, but well, I mean, they could have similar use cases, frankly. They're both classifying. Expand on the variance and bias trade-off. So when we're thinking about trees, the variance is the variation between individual trees, and the bias is, you can think of it as like the accuracy. So if you were building a one tree model where you're trying to say classify something, and you built it to have minimum bias, you're going to have very high variance, and it's not going to generalize well to other data sets. But this is the same rationale to when we're building random forests, where you can then use that variance to cancel itself out if all things work out properly. I'm trying to think if there's anything else on bias and variance. I don't know if anyone has any other inputs from the team. And again, if anybody has any questions, feel free to throw them in the Slack channel, and I or any of the other team members will be happy to answer them. You can always reach out on the other Slack channels after the course, or feel free to reach out to us on LinkedIn or any way you can find us. That's all I have. So if there's no more questions.
No, there seems to be no questions right now. Okay, thank you very much, Tim, and thank you, Carolina. Yeah, and I'm looking forward to see all of your questions or comments in the Slack channel. And next week's we have 3 presenters. Okay, see you.
Thank you.
Thanks, everyone.
Thank you, Tim. See you.
Bye-bye.